Right, I think I'm streaming, and as usual, I'm going to, if I can, on here, viewing live. Okay, upcoming, it says upcoming. View live in control room. Go live. Okay, so we are live. I'm just going to hit a hello message. Hello, there we are. So there's a hello message, and I'm also going to publish this on the social media platforms. I'll at least attempt to publish it on one of them. So I'm going to actually, if I can somehow get a link, like a shared link or something, which will be, I wonder if I can get a shared link somewhere. Oh, there's a share. So share and then copy this link. And I might actually even paste it. I'll go here, which is, I don't even know what is in this test folder, the hello world. So just for now, although I might keep pasting this link into the platform, that's actually the shareable link, and I will zoom in as well. Plus, I don't know if this is going to be a Python coding session or something else, or a deep learning lesson. So I'm not even going to call it a lesson because this is quite interesting. I'm going to do something different, and I believe I should be saying, if you're not interested in being bored to death on deep learning, then it's possibly worth switching off. So only if you want to look at or follow deep learning, because I'm going to basically be going through a book, and the book is going to be this book, The Little Book of Deep Learning, which I literally just came across. I've got not very much idea about what's in it at all. You can see me struggling to even open it, and it is actually designed, because I read the first like 5 pages, and there's like 160 pages as I need to go through. It's said that it's for mobile applications, which is why it's the little book. But it's actually quite cute, because there is another little book. Um, you get all, like when we were kids, you had all of these books were like sort of like tiny books with like great prophecies, and they sort of like came in these handheld things. So this is the Little Book of Deep Learning. I don't know the professor that wrote the book or very much about it at all, so I'm going to be going through the whole lot on that, and I'm literally going to post I guess it's still called a tweet, but it might not be soon. So I'm just going to put live on YouTube now, and basically I'll paste the link in there, and actually also this is the little book, so I'm going to copy this because I might publish this a bit from time to time as well. I'll make a new text file as well, so it's called The Little Book of Deep Learning, which is all going to be on one line of thing. And consider this to be, you get ebooks, right? So this one's going to be I'm going to call it an iBook, right? So what's the difference between an ebook and an iBook? An ebook is one that is read to you, and you can't like listen to it before you fall asleep, and an iBook is one that I'm still going to read to you, and you'll fall asleep, but I'll probably do some coding somewhere in the middle of it because it's about something interesting. So every now and again I'm going to take this link and publish it. Sometimes in the last one, or the previous, not the last YouTube video that I did, but the previous YouTube video that I did before that. It's not even a YouTube video, I guess it's a live cast. And the live cast I did before that, I don't know, it peaked at about 20 followers, of 20 readers. That's not very much at all. I'm sure if I was doing something else, in fact, if someone else was doing something else, there'd be like 20,000 followers. But yeah, this is very nuanced. So only if you're into deep learning, and if you remotely want to even see what this book is about, then I'm going to be reading about this book, The Little Book of Deep Learning, by Francois Fleuret. I presume that's how it's pronounced, from the University of Geneva. And here we see, I guess, a couple of like layers or neural networks or something like part of a neural network, and we shall delve into it from there. So Francois is a professor of computer science at the University of Geneva in Switzerland. this cover illustration is a schematic of the uh, neocognition by Fukushima, a key ancestor of the deep neural networks. But actually, those of us who've worked in finance know, or actually engineering, or those of us who are around, I think it was the mid 2000s, we will know Fukushima. Unfortunately for Fukushima, for something else, which was the nuclear reactor. There we go, top link. So it's not the same Fukushima, but basically the Fukushima nuclear disaster on March 2011. So that's when it was. I remember it quite clearly, actually. It was caused by a tsunami, and the tsunami flooded the nuclear power plant. Essentially, that's what it did. I'm just going to shift control plus. There we go. I'm just going to zoom in a little bit. There's this nuclear accident that flooded effectively the power plant, and so it's a different Fukushima, fortunately, a better version. So, and yeah, the heating systems or something, or all the controls went out because it got flooded, and nuclear like waste or whatever went all around. So that's not what this is about. This is the little book of deep learning. There is actually a URL here, but also I've just got the actual like downloadable file. I can like flip this on and off, but basically, well, if I can, is this the piece that does it? That's the thumbnails. Maybe that's the bookmarks. As part of it, yeah, we're going to look. I think it's quite helpful sometimes to have the bookmarks, so I'll keep them open on the side. And it does say here that this book is formatted to fit on a phone screen. So, and literally, I've got knowledge of like deep learning and neural networks to an extent, but I haven't touched things for a while, so it's actually a recap for me. There's going to be lots of new stuff in there. You know, we're literally gonna have a look at the contents now, and I'm actually just going to basically, I think I'm going to sequentially go through the book, unless anyone's got comments on that. So, you know, I'll see if anyone does kind of like link in or have comments. Otherwise, I'm just kind of like going to read through the book as it is. So, but let's just start with the contents, because it's a good place to start anyway. Which list of figures and foreword. So it'd be interesting reading the foreword. That's going to come on page 8 anyway. What page we're on? Page 3. So just to get an idea of really what this book is going to be going through, and I'm kind of like using this as a template rather than, you know, it's just kind of like a sequential. It doesn't mean it contains everything. It doesn't necessarily mean it's right or wrong. You know, I could bespokely, I guess, do my own tutorial, but it's just nice that it's like this. So, you know, it's kind of like, let's have a look. I would have been reading this type of thing anyway. It's of interest, so let's just see where it goes. So it talks about the foundations. I don't even know what would be considered to be the foundations, but then it goes into the first chapter, which is machine learning. I've got my own like opinions and versions on machine learning. Learning from data, okay, that'll be interesting. I've done some lectures and stuff myself on these, which is talks, lectures, I don't know what you call them. So it'll be quite interesting. Then we've got basis function regression. Now, if it's linear regression, I guess, if it's referring to that, or logistic regressions or some sort of regressions, that, you know, I think I'm familiar with those, so we'll be familiar with that to some degree. Again, this might take different angles. And then under and overfitting, that's quite important. A lot of what is like machine learning and AI and data science and all of this, really, like, it's actually, we might have called it back in the day just statistics, because under and overfitting are just statistical things in reality. They manifest themselves, so there's a very close linkage. It's I don't know, nearly like wasps and bees are kind of like related in lineage. So there's a very strong relationship between statistics and everything that kind of like migrates into, you know, machine learning and all the rest of the stuff that goes below. Then we've got categories of models. Again, I've done talks on this, and there's a huge variety of categories of models, but it's kind of like, yeah, there's like classifications and other things. So maybe it doesn't seem like it's that long. I don't know if I'll open up my own presentation, but then it might be too long, so I'm going to possibly try to read through the book, because it looks like it's only 2 pages on it, so we'll see what it says. The next chapter is efficient computation. So, I mean, this is quite important because at a certain point, I'm going to be coding on this application, which is, let me get the right one up, which is VS Code. So I'm going to be coding here, and that's actually on my own PC. And, you know, it's limited to the CPU or GPU if I have one on the PC. The GPU is the graphical processing unit, so we'll go and have a look at what that actually even is. But then we got it's got GPUs and then TPUs. So we've also got CPUs, which is a central processing unit, so the normal kind of like chip on our computer. Then there's graphical processing ones. Then there's specific processing units that are TPUs, that are tensor processing ones. At least we're going to be taught, or at least we're going to read a bit better than my opinion on that. So we're going to get to that. And then it's going to go talk about tensors, which fits in with that, which is kind of like the purpose of it, because some of the computations become heavy, and that's the whole purpose of it. But these TPUs, is it tensor processing units? Probably that actually, yeah. But these TPUs, they're specifically designed for crunching data for tensors. They're very efficient at that. So that's kind of like what this, at least a hint to what efficient computation is. But we'll see that in a little bit more detail, I guess. Then we've got training, which I presume refers to testing and training. We kind of like, you know, the standard model is to split your data into a training set and a test set. And I think most of it goes on to training, like 75% to 80%, whatever your choice is, and then use the last part for actually testing. Then there's losses, so I guess loss of information. We'll go through that. We'll be told there's 4 pages on losses. Auto-regressive models, gradient descent. So that's kind of like, you know, again, hopefully we'll see better than what I draw, but gradient descent is kind of like very simple thing where we want to find our minima, and the gradient descent is kind of like, you know, oops, let me try and draw a straight line, but it's sort of like we're going that way because we're going downwards, and here we're still going downwards but at a lower rate, and kind of like we're in the bottom, we're still going downwards but not so much, and likewise here we've got gradient descent at any point here, so it's kind of like going downwards, and it's sort of like finding its like minimas or maximas effectively. So that's what gradient descent does, very crudely. That's what it does. Then it talks about back propagation, which I think is really, really interesting, and it's a big, big factor. But basically, you do your computations, but then you have to do backwards calculations. So that's called back propagation, which sometimes I nail, and then other times I get stuck on. So maybe I'm even going to attempt. That might be the attempted failed Python bit that I might attempt to do. Everything here is live. That's the key. So if I am an R a lot, it's because I haven't thought about one single bit. I'm literally reading this live, and I'm going to code live. So I massively, if anyone's got any input or help, that would be massively useful. And I'm just going to check actually. Yeah, okay. No one's actually picked up the tweet anyway, so that's fine. The value of depth, training protocols. So I'm wondering what the value of depth exactly is, but it's possibly something about the maximas and minimas again. Training protocols and the benefits of scale. So is that the benefits of just bigger data, which possibly it is. So we'll see. So we've done machine learning, efficient computation, training. Then we go into, and they're all covered effectively in this. I presume this is the foundations. And then we move next into the deep models. So I guess this is going to become a bit more complicated, should we say, possibly. So deep models, and we've got model components. That's going to be section 4, model components. The notion of a layer. I'm presuming this is a layer in a neural network. Linear layers, okay. Maybe we can handle those. Activation functions, we kind of like know very, very broadly speaking what an activation function is, but I guess the book will describe it quite nicely, which is something like this, which is we have sort of like this decision curve sigmoid function if I draw it right, and at some point it's either got to be kind of like my childish attempt to draw, it's sort of like got to be a yes or a no, so it's sort of like a 1 here, or a 0 here. We've got to get our answer, and it's kind of like based on like these things. At some point we're activated to say yes or no from our neural network. So that's what that is. So hopefully I get to learn a bit on that. Then it's pooling. I'm not sure I've heard of that. Dropouts, I think I've heard of that to an extent, but we'll see. Again, they're probably related to the activation functions. Normalizing layers. Normalizing is a very big process, full stop, in statistics. You should be normalizing your data. Kind of my best example, or like sort of like crude example, is if you are looking kind of like at 2 sets of exam results. Again, you're kind of like there, and all of this class kind of scores really badly. So sort of like there, and a few people score well, and then you compare that to another exam over here, where I don't know, everyone scores sort of like average, so they're all in the middle. And then you imagine yourself like where you are, and you kind of like score here, and you didn't do very well because no one did well. Here's 100%, and kind of like here's 50%, and you scored less than 50%. You're disappointed. But then when you get normalized relative to the class, you kind of like I'll get to that point. But basically here, if you're so like normalized, so you come in at this point. You scored kind of like 50% or 60% because the middle was about 60%. But in both cases, when you're normalized, this one you're normalized and you kind of like stay where you are. But this one you're normalized, you actually feel like this. Imagine that this got recalibrated to something like this. Then your normalization will be up here, and you actually scored better in real terms on this test relative to your cohort than you did on this test. So that kind of like that movement was kind of effectively the normalization process to an extent, and it needs to happen because otherwise you just thought you did badly, but you didn't do badly. You did actually better than you expected relative to testing. The same thing works vice versa because you could do worse than you expected. So normalizing layers, that's my crude version. Normalizing layers is going to be more complicated, I imagine. Skip connections, I'm not sure of. Attention layers, I've the attention layers in token embedding that's part of, I'm going to say, part of the revolution of sort of like chat GPT and AI. I'm just trying to recall exactly, and maybe if somebody is watching or if you want to post a thing, I'll go and possibly have a search for it later. But the original GPT model, which was written by several people, and most of them out of Google actually, was something like it's all about the attention or something like that. Token embedding, that's part of the sort of like mathematics or of the at least in natural language processing of sort of like taking these words out. It's called tokenizing and turning them into tokens. So I imagine that's what that's about. And then positional encoding, which might be a similar thing, which is where the words are in terms of sort of like the sentence and the value of words. So certain words come after other words. And this goes back probably, I mean, we were looking at these kind of things when I was at uni 25 years ago. So it really does go back in terms of like coding, encoding, decoding, encrypting messages, because certain words come after other words, and you can sort of like look at the probabilities of these things. And I wonder if I just take a normal sentence, but if I said hello in computing terms, someone will, what's the next most common word, and it might be world because everyone does hello world as a program. So the tokenization or the positional encoding might lead us to believe that the next word is hello. It might not always be that. It might be sort of like hello moon or something else, but hello world is a very common thing. So then it moves on finally. So this in the deep models bit, which is the section 5, is going to be architectures. So I guess we'll look at architectures. What I will do is possibly another tweet or retweet. I've been saving myself for tweets. Let's just, but I will bang out another tweet somewhere if I can find it. So let's put it out. And again, so excuse me jumping around for a little bit, but basically I will go back to, I might even post thing here. I might make a new Python file because I don't even know what we're going to do yet. So we could always rename this our main file .py. There we go. And I'm just going to take this stuff here. And there we go, there's a hello world. I was just talking about it. Maybe I already saw it, so I had to had it in my mind. It's our main file, and we just do some comments there. Literally don't know where this is going to go with any of this stuff, but basically this is like the YouTube link at least. So, and really, actually, it's going to be, this whole section, I guess, is going to be either Python, Python, Python programming, or deep learning, artificial. If I spelt it right, I'll get all of the typos anyway, because hopefully they'll come up. I'm just going to kind of post that somewhere into onto our social media platforms and see if that live on YouTube now. Tweets, there we go. It's back up there. So anyway, we've got kind of at least part of this is going to be this is a link to the same video that's been created. So, and I will do templates. So there we go. I don't know if we're going to be doing coding or not. We might just read the book. So, but there is a template there ready for us if we want to do it. So let's move on. We go on to architectures. So multi-layer perceptrons. I've read this so many times I've forgotten about it. Convolutional networks. So convolution is a word in science where, well, effectively you sort of run one function over another. It's almost like a multiplication of functions is the way to think of convolution. What does that mean? Because I just kind of said it. If I can squeeze it in here somewhere, is that if you've got this function, it's like there, and you want to convolve it with another function, so I don't know, like this one here. It's kind of, and what it means is you drive this function, so this function here, we drive it over that function. It's kind of like the area under the chart at every point in time as this one kind of moves forwards in points in time. That area under the chart is the convolution of those two different functions. Now, if you had two normal distributions and convolved them, you would still get a normal distribution. And then the last bit is attention models. I think that talk when I was talking about was something like attention is all you need. When I started talking about attention layers, there's a great paper, and I think it's something like attention is all you need. So, that's AI isn't new. AI is quite an old concept, a very old concept actually, but there's been very, very big recent developments, and the large language models probably led mostly by ChatGPT to start with, although I have at least 4 of them on my system. I've got ChatGPT, if I open it up, welcome there, and I don't know even if, we'll get to that bit, I'll have to log on and do all of that stuff, but it's ChatGPT. Then there's another one, Google Bard. You can see I've been using it. It's great. You can ask some questions and it gives you some answers. Sometimes it gives you answers that are good, and other times it gives you answers kind of out of the large language model that aren't so good. And the latest one, which is, here we go, so linked list in Python, I don't know, which is our, funnily enough, I'm not sure that this one did, but that's Claude. It's just another large language model of the large language models. So you can have all kinds of fun with them, but they're great for coding. So anyway, we move on from that. That's what the architectures is about. Then next, that's all of deep models. So then we're moving on again, I guess, which is applications. I'm presuming this is kind of a bit more real world, which is, so we're going to do the understanding in the maths, and probably looks like some of the older maths and stuff. It looks quite focused actually, to be fair. It looks like it's going to be possibly a good book. We'll see. Can't judge a book by its cover or by its what do you call it, by its contents, the list of contents at least. But let's see what the actual content is. But basically, this migrating down applications is kind of as in it looks like it's real world applications. Hopefully, because the reason I say that is I see image. Okay, image denoising. I don't even know what denoising is, so that's going to be new for me. I'm going to cheat a little bit and jump forwards and just see what does denoising actually mean. I can run over the Fukushima thing because we don't need that up there. So paste is an advanced technique used to decrease grainy spots and discolorization. Okay. Again, like I didn't know what that word was, but I was literally doing this at Imperial College 25 years ago, although we weren't doing it to the same volume of computation or the same number of pixels. So we had sort of like, 1,000 pixels, in 100 by 100 grid or something like that. 100,000. Make sure that because 10 times 100 is 1,000, so it'd be like 10,000 pixels on our grid or something. It's 100 by 100 grid, or it might be like 500 by 500. But now we get things that are like 15 megapixels, which is 15 million pixels. So the granularity and the mathematics broadly stays the same, but the computation or pretty much the computation actually is sort of like where it goes, that increases. So anyway, we see on the side here like noise reduction and stuff. So there's other things. There's really interesting stuff like edge enhancement. I might try and do some of it if there is any. If I do get to do any coding in it, there's things like edge enhancement and other things that we do, and all of the nice things that you see on those apps. I don't know, like Snapchat and things where they process your images quite nicely and put a pair of glasses on you and all the other funky stuff as well. A whole bunch of stuff like that, or I don't know, put fire on your head. So that whole section is called image denoising. We used to call it digital image processing, but here it's called image denoising. I wonder if I can put comments on there. That'd be my signature, which is not of much use. Let's have a look. Yeah, don't really want to do signatures. But can we write text in there anywhere? Sign it by. Oh, you can. There we go. There. So something like digital image processing. Smaller, 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 smaller. There we go. I wonder if I could change the font color on it as well. Yeah, you can. There you go. Purple. There we go. Red. So it's my version, so we know that. I'm just appending what was there, kind of. So I've got a little edit section too. So I wonder if I can make that smaller. Yep, you can. That's kind of like what that might be. Denoising, that's the word for it. Image classification. So is it a cat or is it a dog? Is it an apple or is it some other fruit? Object detection, squares, triangles, presuming it's that kind of stuff. So this is all actually quite practical, and I've written a book on it. This kind of stuff. Which I might pump the book. Python links. There we go. Click this button. Python programming. Yeah, go buy that book. It's actually quite interesting, the contents of it, because it goes into some of that image processing stuff and what you can do. Some really cool things that you can do in only 100 or 200 lines of code in Python. I might try and get to it or nick some code from somewhere from that. So like interesting stuff that you can do, like object detection quite fast, where you sort of like wave your hand, and I actually show that in the middle of the book somewhere in some of the pages, and also like there's quite a nice fun game where something like this pen, if and I did it with like a green pen and like a red one, where you can sort of like move around and you can get this dot following you, but you can actually draw on your screen with it. So which again is used for a lot of the games and stuff. Then there's object detection, which is similar. Semantic segmentation, so again something that I've not necessarily heard of. Or do I have to untick? No tick marks. I wonder. Close this section. That close it? Yeah, it does. I wonder what segment. You know, I'm not going to like go into all of these too early because we're going to get to it anyway. But I don't know what semantic segmentation is exactly. Segmenting is breaking things up, but I'm not exactly sure what's being broken up. And then we've got speech recognition. So again, I've had a little play around with some of those. Text image representations. Okay, we'll see that, and reinforced learning. So different type of learning. I've done a couple of talks on that, but yeah, this will remind me at least. Then it's a synthesis, so text generation, image generation. Some of the things that we're beginning to have, like if you go on like Google Maps, for example, um, you say like navigate me to. Well, I've started to do this quite a lot, like navigates me home. That's not the most complicated of commands, but you couldn't do that 10 years ago. So navigate me home, it's got to pick out the navigate me, and then home, it's got to identify where home is. Then it kind of like pumps it into the Google Maps, and it sort of like switches on the navigation and sends you to wherever the home address was. Or you could say navigate to a certain address, and it'll go there and sort of like know which part of the sentence to do the lookup and so forth. So there's things like that. Also text generation is kind of, you just talk and then it generates text for you, so all of those dictating things as well. So just stuff like that, I guess. And I'm just trying to make sure if there are chats, because I can do, I think somewhere, is it docs chat, the little chat section, which is kind of like here, so I can see if anyone chats. I'm actually going to stick in a hello. I'll keep it by my side somewhere. Now I've got 2 hellos in the chat, so that's it. Then it's got missing bits. I presume that's whatever's missing. The bibliography, well, that's recognising all of the other people. And index, I wonder what index is, because I thought this was the index. Oh, it's obviously something else. And that's kind of like it. So list of figures, that'll be interesting. That's a good place to start with. So what's in our list of figures? Kernel regression. I'm presuming this is just images of stuff or what we're expecting to see. Overfitting of kernel regression. So we've got that over there. That's overfitting. Casual autoregressive model. Gradient descent. So probably where we... Oh, this is probably all of the in scientific papers and so forth. This is kind of like wherever you've got an image. I guess these are all of the images that are part of the text. So that's what it is. So there's something on back propagation. So I could kind of like click on it and we get something that I'm actually quite scared of, because I've just seen it for the first time and I was hoping it'd be a nice cute image, and it's not. It's talking about Jacobians and backward propagation. So hopefully we will learn in that capacity. Now, can I go back? I'm not sure. So let's just go to list of figures again. Gradient descent. Oh, well, that's back like a gradient descent. Another one. That's a little bit clearer. Maybe we can sort of like, at least my rubbish version, maybe it's illustrated a bit better. I might draw on the drawing. So like, kind of like imagine that you're on a hill. You're sort of like heading, that's the world's worst arrow, but you're sort of like heading this way. It's like downwards. And there you go, you got sort of like down to the bottom of the valley nearly. I don't know if this one's a lower bit, like sort of like down here. Is that the lowest point? But if you were sort of like, at least if you were over here, at this bit, I should use green because you would expect to sort of like fall down the hill that way, and if you were somewhere up here, that you would again sort of like expect to like fall down this gradient, your descent down your gradient. So the version that I drew was like 1-dimensional, and this is 2/3, or I guess you've got like this surface, which is it was 2-dimensional, 3-dimensional because it's got an X, Y, and Z component, at least visually for us. So gradient descent. But anyway, let's just go back to our list of figures. We're going to come around and see all of those. So feature warping, training and validation losses. I'm expecting to see some sort of loss function or something. Yeah, that's quite nice. Expecting to see that. That's a bit more understandable. we're not going to be scared of any of the maths. I'm going to have a bash at it, even if I get it wrong. I'm hoping people will join at that point and tell me other stuff, but I'm going to read through it. Everything is doable. Like, everything is doable. So convolutions, you know, I hope my description was sort of like nice. Possibly we're seeing like a digital version, I think, of the convolution, so that's interesting. 2D convolution, okay, same thing, passing cubes for each other, fair enough. So it'll be interesting again to see at least some sort of understanding of that. Stride, paddling and dilation, I don't know, we'll get to see what that is. This is all our list of figures. I like to see lots of figures because that helps us. A picture paints 1,000 words. So a formula scares everyone off, and lots of words are just lots of words. Max pooling, dropout, batch normalization. So I guess we're going to come across most of these. You know, we'll see them as the pages evolve and what we're going to get through. Multi-layer perceptron. Yeah, okay. I've got my bottle of water, which is here. You know, bottle of water somewhere. And a cup of coffee, which is beginning to get medium in temperature. So, oh yeah, definitely like, follow, subscribe, because it's just helpful. Post your comments and hit more likes again when we go through this, because it's just helpful. It's kind of like helps, I don't know, the channel or whatever. I don't even know if anyone will or won't watch, but it would be quite nice if you do. And okay, transformer GPT model. So GPT, okay. General pre-processing transformer model. Maybe we'll get to have a little look at that. Object detection with presumably SSD, solid state device, possibly, which is, you know, is it with a CCD array of your of the camera, or is it something to do with the hard disk? Not hard disk anymore, the solid state disk, basically. Semantic segmentation with PSP. Don't know what that is. I won't click on that image, although we could. We'll get to that. Clip zero shot prediction, DQN again. I don't know what that is, so we'll come across it. I don't know what the acronym is, so we'll find out. Few shot prediction with a GPT. Again, not sure. So we move on. We get to the foreword. I could actually get the PC to read a lot of this out, but maybe I'll just read it myself anyway, because the whole point is that I'm trying to read it too. The current period of progress in artificial intelligence was triggered by Krzyzewski et al. Showed that an artificial neural network with simple structure, which had been known for more than 20 years, could beat complex state-of-the-art image recognition by a huge margin. Simply by being 100 times larger and trained on a data set similarly scaled up. Okay. The artificial neural network with a simple structure could be state-of-the-art image recognition. Okay, that's interesting. I guess we had before, you know, any kind of neural networks. You know, we still had a method for like image recognition. So, for example, if I was to draw something like this, because I think that, in fact, I might revert to not always doing the drawings over there, but I might revert to drawing here, which is our little tool over here. The question is this, really, in a way. I don't want that. I actually wanted to draw, not, yeah, just sort of like a box here. So if I've got a box here, and then I've got on top of that box kind of like a circle, there are different ways that we could approach this. So let me just, I wonder if I can fill the area, there we go, and make it different color. But this red circle over here, it's kind of like, you know, what is it? Oh, I've probably done the worst color because it's glaring in the face. Area. Remove the glare, so I make it light. There we go. So this yellow circle that's over here is kind of like, can we detect that this is a circle? Now, there's like lots of mathematical ways of doing it. You could sort of like maybe draw a vector down, and I'm just thinking off the top of my head, so like I'll do it with an arrow, so like go downwards, there's nothing there, and then scan again downwards. Let's do it again over here, and it sort of like stops there and continues. So like then it detects yellow, 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 and then it gets to continues afterwards down here. It's like then it goes blue, blue, blue again, and it gets to the end of the page. So something like that, and again, it does it. It's like over there, and we could infer just because of the size of these kind of like lines that if these lines are, I should sort of like draw this one in context at least over there. But well, I'll keep it at the same height. Doesn't matter. In fact, what I can do is I'll increase the square to be that size. There we go. But if these lines are getting smaller and smaller, so that this gap is getting bigger and bigger, so like if I did the counter line in the middle, which is something like that, and I'll sort of make it red. So make it red there and make it thicker. But if this red line there we go. If I detect this pattern just from a standard scanning, and also potentially scanned horizontally, so and just rotate that, so kind of like that, right? If I detected this type of pattern, and I will just do, because that's the same, from my scanning process, I didn't need a neural network to infer that that was a circle per se. I actually know to a reasonable degree that this is kind of like, so imagine that there was more of these lines going down and across. I could infer that this was probably a circle if I was attempting to look for a circle. So that's image processing, which is a neural network, kind of like learns it on its own or does its own stuff to categorize it to a circle. So that's what this paragraph I think is kind of like talking about, basically, that these neural networks at a certain point, once it's trained, are just better at doing this image recognition. Not only is it better, but kind of like imagine that you had this, and then I could copy the whole lot down, but copy paste. So like move that entire block down below, and so we'll sort of like do that same process, but now we won't make it a circle, or maybe we will make it a circle, but let's have a go at this. We'll sort of like make it a smaller circle and put it over here. Well, so like what happens to all of our process? Like, and if it was a circle, it's fine, but what if it's a triangle? Should kind of like, I was going to draw, let's see if I can get another shape on there somewhere. Right, we can see the complexities that might come out of this. So like, what if it was a color fill? I wonder, fill color, there we go. What if it was like a green triangle? Could we detect that? Now all of a sudden our image processing only for like certain things. Well, again, we could put our patterns and our lines and sort of like detect it. The image processing could do it, but if the neural network is working the way our brains work, maybe it detects it a little bit better. So I believe that's what that is in that page, or that first paragraph is inferring to there. And I'm kind of like going through this. I guess I'm going through this slowly-ish for two reasons. One, I'm scared to get to the harder stuff. Let's not be scared. But the other bit is just to be complete on it, like sort of like an understanding, like a full understanding of what it is. So this breakthrough was made possible thanks to GPUs, graphical processing units. I actually read that as GPUs. I should have read it as graphical processing units, and then the acronym. Mass market high parallel computing devices developed for real-time image synthesis and repurposed for artificial networks. So these things are basically, these are just chips basically, but they're not just, so they are chips, but they're sort of like customized and basically made in a way that they're highly efficient in the process of so they're built for parallel computing. And they're also good for all of this real-time image analysis synthesis. They're very good at like operating on tensors, so that kind of thing. So that's kind of like, that's where all of this has come from. And again, I've never actually mentioned this, although also I have mentioned it, which is, I feel I mentioned it, but I've never gone to the web page of it. But basically, Moore's law, you know, we've kind of like benefited. Moore's law is the observation that the number of transformers in an IC doubles about every 2 years, right? That's kind of like an observation that this scientist, was he called, Robert Moore? I can't remember, but this scientist whose surname was Moore, who is named after, like, made this observation that our kind of computing power is doubling and the cost of it is halving every couple of years. And everyone said, yeah, that's true. You know, that's going to be true for the next, you know, that's been true for the last decade. And, you know, it's going to run out at some point in time. But it hasn't done. Our processing power has become immense. And it kind of like, if I can pull up one of these charts that are good. That's not really the clearest one. Maybe this one here. Wonder if I can zoom in on it. This is quite a century of Moore's law. I'm not going to go into the whole bit of Moore's law, but it's quite an interesting thing to do, and I can't cite it. Just do continue reading. I don't know what happens. That's fine. But this bit here, which is Moore's law, you can see the numbers here, 10 to the naught. And I think 48 years of microprocessor trend data. Okay, I'm presuming this is like, or you could at least analogize it to the number of chips that were available, or like logic gates are available. So yeah, well, it actually says number of logical cores, number of logic gates. But basically, we've had these different techniques that have gone on. A transistor is a switch, like an on-off switch. And we started with these massive transistors, and kind of like, I think the first one was actually at Imperial College, because the professor said they're really proud of it, and they rolled it in on a wheelbarrow. But now in our standard mobile phone, which I can't, or I can wave it around, but you know, our standard mobile phones here, there we go, the sort of thing that you hold in your hand, which is only a couple of £100. This isn't even a good one, but it's got more processing power than the entire moon, so it's got like millions of transistors inside it. So in the 1970s and 1980s, you know, you had like, you know, 1, 10, 20 transistors. If you had 100, you were like, you know, you had the best computer around. And then by 1990, like, you know, there was things with 1,000 transistors, 1,000 switches. Oh, look, you know, if you compare that to that, you know, so like, and you can imagine this growth, but this is growth is on the order of, each one of these is another factor of 10. It's powers of 10 here. So this represents 1 million transistors, and this represents 10 million transistors, or, well, sorry, 10 million times by thousands of transistors, so like 10 billion transistors, like huge number, more than 10 billion transistors. So like 100 billion transistors, just a huge number of transistors. 10 to the 7 times 1,000, which is 10 to the 10. 10 to the 9 is a billion. 10 to the 10 is 10 billion. So 10 billion transistors is kind of like what that represents. So huge amount of processing power. So while the mathematics existed, the computational power until that point didn't exist. I'll leave some of these tabs open, but I might close them later. So let's keep that open. So that's kind of like what this is talking about. Since then, under the umbrella term of deep learning, because deep learning means, it's kind of like, I think it's a whole category really. Innovations, this whole category, I believe, encompasses, because some people do these sets and things, like, so like they draw these circles as what contains what. I can't remember which way round they are, so I don't want to say it. Maybe if I type in deep learning, kind of, I wonder if deep learning versus machine learning images, sort of like, will I, yeah, there we go. it's kind of like looking for this sort of thing here, which is reminding myself again. Oh, I didn't want that one. Okay, let's just go back to the image, unless that image is in there. So the image is in here anyway. But basically, you've got AI, then you've got machine learning, and then kind of like deep learning. So like AI encompasses everything, and then machine learning is sort of like inside of that. And deep learning is a subset of machine learning based on artificial neural networks. Machine learning, which is this middle blue layer, focuses on enabling computers to perform tasks without explicit programming. So kind of like the beginning of learning, basically. And AI is a science devoted to making machines think and act like humans. Our neural networks. We've got, like, imagine that you've just got a computer in your head. It's a messy one, quite a powerful one. Millions of neurons, billions of neurons. Um, they're kind of like connected in some way. With, we're replicating that process basically. So that's kind of like broadly what that's talking about. So since then, under the umbrella of deep learning, we know where it lies in our picture of things now. Innovations in the structure of these networks, the strategies to train them, and dedicated hardware have allowed for an exponential increase in both their size and quality of training data they take advantage of. So we are now working on big data, like as in the biggest data that we've ever seen in mankind. The collections of data that you can only really harness from things like the World Wide Web. And what it's collected over its course of time, and also the speed of collection, like financial data, or like if you're looking at imagery, the actual volume that you can get from even one single camera, let alone the volume of cameras that there are around the world, let alone one country. Huge amounts of data, 8 billion people on the planet, very large social media platforms, things like I guess Facebook and things that cover like 2 billion users or something like that. Probably 2 billion daily users, and so like 4 billion users in total, across their different things. So all of those sorts of things is big data stuff. So all of this has resulted in a wave of successful applications across technical domains, from computer vision to robotics to speech, natural language processing. Although the bulk of deep learning is not difficult to understand, it combines diverse components such as linear algebra, calculus, probabilities, optimization, signal processing, programming, algorithmic, and high-performance computing, making it complicated to learn. The reality is all of these pieces on their own are actually quite simple. Maybe piecing them together is a bit harder. Linear algebra, y equals mx plus c. It's kind of like, I'm not going to belittle it. I wonder if I can, you can underline text. That's quite nice. I'll start underlining things. I actually wanted to write, not underline. But linear algebra, if I can do some writing. So again, so I get the writing thing up. Is just literally y equals nx plus c. We're starting off at something like this, so really not complicated at all. And then it kind of like evolves. So that's our linear algebra, and maybe simultaneous equations and other pieces, bits and bobs like that. So let's move this to the right position. There we go. Calculus, probabilities, okay. We'll get onto those in optimization and so forth. So yeah. Do I have to keep closing this every time because they get annoying? But I think possibly I do. Let's scroll through anyway. I think I can just keep writing. Instead of trying to be exhaustive, this little book is limited to the background necessary to understand a few important models. Good. We'll never cover it all. This proved to be a popular approach, resulting in 250,000 250,000 downloads of the PDF file in the month following its announcement on Twitter. Great, there you go, and now you got a video as well. It's actually got quite a cute little name, which is LBDL, the little, let me just make sure I get it right somewhere wherever I've written it. The Little Book of Deep Learning, because I renamed it, the Little Book of Deep Learning.pdf. There we go. And yeah, this guy wants to, the writer of it wants to estimate the number of readers. So part 1, foundations. Let's go through machine learning, chapter 1. I'm going to be reminding myself of a lot of stuff, I guess. I wonder if I'll be pulling up any Python code. I don't know. We'll see. Machine learning. Deep learning belongs historically to the larger field. I think I will interrupt myself very quickly before I even start. Possibly. Okay, it's going to be descriptive to start with. I wonder if we're going to get to code stuff or not. It'd be nice to do some coding. Maybe I'll break into coding at some point. But it looks as though it's taking a mathematical and descriptive approach, so that's fine. That's the way we'll go. Machine learning. So deep learning belongs historically to the larger field of statistical machine learning. Okay, that was those concentric circles, which is these things here. Deep learning belongs inside of machine learning, which belongs inside of artificial intelligence. As it fundamentally concerns methods that are able to learn representations from data. The techniques involved come originally from artificial neural networks, and the deep qualifier highlights that models are long compositions of mappings. Okay, so that's what the deep hive or deep learning, now known to achieve greater performance. So yeah, that's kind of like where it's embedded. The modularity, versatility, and scalability of deep models have resulted in a plethora of specific mathematical models and software development, established deep learning as a distinct and vast technical field, and it is absolutely humongous as a field. There are a whole ton of things, and I've done some of that stuff in some of the videos, but I haven't even touched. So one person can't touch the surface. We are standing on the shoulders of giants. We're really standing on 50 years of history, if not more, maybe even 100 years of history, and certainly and hundreds and hundreds of man hours of work or people hours of work, thousands of very smart and dedicated people. So we're kind of standing on the top of all of that. The simplest use case for a model trained from data is when a signal X is accessible, for instance, the picture of a license plate, from which one wants to predict a quantity Y, such as the string of characters written on the plate. So, our simplest case really, which is, we go back from here, let's create a new one of these. But we've kind of got our image, and imagine that is just an image of God knows what. And if I can pull a general image, just a picture off the web, but the sky and background, I actually might do that. So let's see if I can get that. I'm going to pull this out of here, so somewhere. There we go. Oh, fantastic. One of these. Now, copy image. Paste our image here. Right. And then, I'll get a car and I'll stick my number plate on it. How about that? Be very crude. Car. Not Carl Sagan, but car. Images. There, find a cartoon one somewhere because it'd be more fun. We've got to be pointing towards us. Oh, here we go. Here's one that actually has that's maybe I'll use that entire image. I don't know. I'm going to draw my own. Let's get a drawing version of it. We'll get a fun drawing version. La-di-da. Okay. I'm just going to copy that, otherwise we won't get anywhere. I wanted one pointing towards us. That's all. Oh, here we go. With a person drawing, hand drawn. Copy image. This is really, really rubbish in a way, but it's going to be. There we go. That's our image of our car. There we go. You got the person drawing. I should remove the hand, but I'm not going to. But on top of all of that, we've now got a license plate. A, B, C, 1, 2, 3. There we go. You got a license plate. right there in our image, and our image has got this background and all the other stuff that's going on it. Make that a tiny bit smaller. So our image looks like that, and can we pick out that ABC 1, 2, 3 from all of the other stuff that's on it? Like we know, like human-wise, we can sort of like detect. We know. Well, you can see already that I kind of like copied and pasted it there. But so like, can we zoom in? Can we get our our car here? Okay, I put it. Our one's in a big blue square box anyway. But can you get your car? Can you zone in? Can you get what should be a license plate, some rectangle at the front of the vehicle? And then can you pull the characters out of it in some way? So can we do that? That's the process of all of it. So where are we up to? Yeah, so that's our the simplest use case for word training is when we got this signal. I didn't mean to do that. Let's get rid of that. This signal is accessible, some way, and we want to get this. We want to pull out from the signal. We want to get our quantity y from that in some way. So in many real-world situations where x is high with a high dimensional signal captured in an uncontrolled environment, it is too complicated to come up with an analytical recipe that relates x and y. Right? We can't do it. So normally we'd say, so like find the top corner of the license plate, and then sort of like recognize it like that. But it's just with the real world situation, with the sky, with all the other stuff behind us, and maybe other cars and other vehicles and so forth. Now it just becomes quite a computationally intensive task, and we need some help to do it. This is what one can do is to collect a large training set, and the training set is denoted with this curly D of pairs, and they're x, n, y, n. I don't even know what these pairs are. And devise a parametric model F, a piece of computer code that incorporates trainable parameters W. So W probably stands for weights, our trainable parameters that modulate its behavior and such that with the proper values W star, it is a good predictor. Okay, good's mentioned in quotation here. Good means that if an x is given to this piece of code, the value y, which equals this function, so this parametric function of x given w, it computes is a good estimation of the y that would be associated with x in the training data set. So we're kind of like looking at this training data and saying, like, we or at least we train our model in some way, and we're hoping that what we've trained in the model is going to actually come about and be what we've trained in the model is actually going to be a correct version of the true observation, and so we train it, and then we effectively, or at least the procedure is to train the model and then test it with the rest of the data. So we take some part of the data for training, and the other part we retain and we use it for testing to say, like, that's our prediction, and then we still got some of the data left. So can we like, does our prediction fit what we were at least hoping for in some way? And these training things, we still like punish it if it gets it wrong, or like downscore it if it gets it wrong, and upscore it if it gets it right, which is kind of like, if you were learning to walk or something, like this neural network. When you fall over, you hurt yourself, and when you don't fall over, you stand up and can pick objects off the table. So we're kind of like it's learning in some similar type of way. So this notion of goodness is usually formalized with a loss, LW, which is small when f dot w is good on D, right? So that was that kind of model. We want to minimize the losses, basically. So we want to get as little losses as possible and as maximum wins as possible. I presume that's kind of like the way around that it is. The training model consists of computing a value w that minimizes this loss given w, or value w star that minimizes our loss given this w star. So we're going to amend these w's to find this w star in some way that gets the predictions better and better and better. That's the goal of these neural networks. I was going to say large language models, but no, neural networks. Most of the content of this book is about the definition of F. Okay, that's useful. Which in realistic scenarios is a complex combination of predefined submodules. So, and just going back up here, F here is our function, but it's a diverse parametric model, which I should go and now click on. Let's hit close over there because I want to actually copy this text, which is this copy, and kind of like again resort to Google. We probably don't need our images or card pictures. I'll keep this up for a tiny bit, that little chart, but basically parametric model, boom, there we go. And parametric modeling is a modeling process. I should just put parametric model in statistics. Here we go on the sidebar. Out of Wikipedia, in statistics, a parametric model or parametric family or finite dimensional model is a particular class of statistical models. Specifically, a parametric model is a family of probability distributions that has a finite number of parameters. I remember doing this back in maths. I think it's further maths, which is A level basically in England. So you're doing it about 18 years, 17 or 18 years of age, where you have parameters and like one function is mapped onto another function. We could go into the kind of like, I wonder if we could. Yeah, we see sort of like, okay, we've got a Poisson distribution, normal distribution, Weibull binomial distribution, so some of these parametric models, but it's actually simpler than that because you could do parametric modeling on circles. Aside from linear regression, examples of parametric models include linear regression and SVM, which I have to recall myself, I did a little video on that, or not video, like a lecture on that, but again, easy to forget those things. I wonder if there's anything interesting there. But parametric model, basically it takes in parameters. That's really what it is. So I think this one here will take in, well, that's got kernel estimation as well. But even a straight line, we've got some sort of parameters and we can't like best fit it. So, you know, they're the parameters. So let's, in fact here, let's just go. Assumptions about the form of the function can ease the process of learning. Parametric models characterized by the simplification of a function to a known form. A parametric model is a learner that summarizes data through a collection of parameters. So, and as an example, let's have a mapping function here, and we sort of like got this B0, B1, x2, and kind of like we got to sort of like guess or not guess, or the better that our and B0s, B1 and B2 are our coefficients, and we kind of like can muck around with those. So the coefficients of the line that controls the intercept and slope of the line, basically. So we can muck around with them and we can fit them as best we can to our data. So that's kind of like crudely what parametric modeling is. So let's just go back. Where were we on our reading journey? We didn't get to that bit. Okay. Right. Okay. We're kind of like here. I just copied the parametric modeling. I think that's where we were. What one can do is to collect a large training set D of pairs xn and a diverse parametric model F. A piece of computer code that incorporates trainable parameters. Yeah, so okay, we went over this and we're trying to achieve goodness, right? And our goodness was minimizing our losses. So we seek this W star, this set of weightings, or something I presume it refers to weightings, where we minimize our losses. So we're seeking where this thing gets to its lowest point, and that's kind of going to be our best guess. And almost so that the lower, the less, the fewer losses that we can have, the more accurate or confident we can be with our prediction of the data. Yeah, so most of the content of this book is about the definition of F, which in realistic scenarios is a complex combination of all of the stuff above, of the predefined submodules. The trainable parameters that compose W, this is like this curly W, could be omega. I'm just going to call it W for now, are often called weights, okay? So they're like, I think they're called weights and biases, but they're called weights. By analogy, the synaptic weights of biological neural networks. So I'm sure that there's going to be pictures and stuff that depict it, but imagine that things go into a system which is basically like this. So like these are decision things, and you know, you sort of like got this outcome or something. You know, these go into, you know, our decision thing here. They might all be equally weighted, but they might not. Imagine that kind of like, I guess it's like if I coloured this one green, like if it had like a higher weighting. So like they're not, like there's 4 of them, so imagine they're all 25%, added up to 100% weighting. Then the decision would, and each one of these, like 3 of these flagged and 1 didn't. Then our signal will be like 3 of these flagged a yes and 1 flagged a no. Our decision would then be a yes. But if we weighted it, and this one was like 75% of the decision making, then the bias would kind of like change. It's sort of like it's a crude example, but that's kind of like what the weighting does in some ways. It's like the importance of the observation. So we know that we can optimize them in some way, but with technique different from those used to optimize W. Okay, let's just, I'm going to go back here and just do a repost just to see if anything does come about of, I think someone's messaged over there. Let's have a look. Yeah, okay. I'm going to paste again. I'm going to do a second post on that. What page were we on the we are up to page well, I'll say 14 because we're just on 13 of 160. So there we go. Just posting that out there. So let's continue. Anyway, we move on. So, by the way, this isn't as hard as it looks. I'm going to try and break it down if need be, I think. Well, it is probably as hard as it looks. Let's have a look. Basis of function regression, or at least I can explain all of these terms. Basis of function regression. So, we can illustrate the training of a model in a simple case where xn and yn are 2 real numbers. Okay, a real number is just 1, 2, 3, 4, 5. Okay, I might get the old pencil out again. So keep getting my signature there. Don't want that useless thing. Real numbers. 1, 2, 3, 4, 5, and so forth. That's our real numbers. A little buzzing sound coming in. And there we go. So it's our real numbers. So we can illustrate a training model in a simple thing where xn and yn are 2 real numbers. The loss is the mean squared error. Okay, so I think this is just talking about, it looks like it's just talking about a linear regression. I'm hoping that is that, because when it goes to mean squared error, that's kind of like generally what you're talking about, which is we've got our little chart somewhere like that, and then we've got a bunch of dots on our chart, so these little dots everywhere, and we want to put a line somewhere where it's kind of like what we perceive to be our best fit, and we look at the differences between all of these dots and a line, and in some way we attempt to compute to minimize this function, and that's that loss that's being talked about here, this LW, which we want to minimize the mean squared error. We want to reduce that as low as possible. So, because that will be our line of best fit. And FW, so we continue, and F dot W is a linear combination of predefined basis of functions. FW with W equals the weightings. Okay. So I guess it's still all quite mathematical there at that point. So our parametric function f of x given W is the sum of from k equals 1 to this number k, this big K, which is the sum of all of these weightings basically. So you've got like a whole bunch of weightings. We've got this weighting multiplied by this function. It's kind of like you'll imagine there was a little time sign in here, multiplied by. In maths, we don't use time signs for like algebra, but WK, so that's our weightings, times by whatever our functions are on this value of x, and our value of x, which is kind of like our observation, and it's the sum of the products of all of these for k equals 1 to n. So it's W1 F1 of x, and then W2 F2 of x, W3 of F3 of x, and so forth, all the way up to our final weighting of big K. Normally it's n actually, but big K, so W big K of the function f of k of x. So yeah, that's kind of like it. Since our function is linear with respect to WK, S and WK to the WKs. Okay, so since our function is linear, so we're talking about linear function, and LW is quadratic with respect to this. Why is it quadratic? I'm guessing that this is referring to algebraically the least square thing that I drew up before. So the losses, I think I actually had it on a different thing, just randomly up, which was over here. I actually did this y0, this y1 minus y0, or at least like the error of any point. So that's a slope of the line. But if I actually nick all of this, which I will do, copy that, kind of create a new page and paste the whole lot down here, and we just take one of these points, and I'm going to move one of these points kind of like further away, just so that we can illustrate it. But its error is kind of like this thing here, from its point to the line, it's perpendicular to the line. So we're going to make it a little bit thicker and kind of like red. But kind of like, how do we determine its distance from the line? Well, it's got this x component, which is going to be copy paste. There we go. It's like its x component here, and it's got its, that's how far its x is from the line. And I wonder if it's a better way of doing that, which is its x component is going to be this one here. Make sure that I do this properly. If any of the concepts get wrong at any point in time, that wouldn't be good, because then we'd be talking about the wrong thing. So that's its x component, and copy paste. It's like that's its y component. Again, do copy paste. There we go. That we know that this line here if we label, and I'm just going to put simple labels on now, that this gets the label of A, colour it red, right? Copy paste. I think you see where I'm going here with all of this, and this gets the label of B. Oops. There we go. So that this line here is going to be B. You know, what is the error, right? And so our error still, I might paste another one, control if I can. There we go. This one here is C, that we're left with a formula down below that basically C squared equals A. I've got to get the squares in and also extend this a little bit out so that it looks proper, equals A squared. I'm going to put squared plus B squared basically. So mathematically speaking, if I can get the squared sign out, which I think I can somehow, text superscript. I could do this computationally and I kind of like possibly should, but if I can get that, there we go, superscript. Got that one there. So you know it's governed by this formula. So this error measure that is being talked about is basically this C squared. And again, if I do take all of this and copy it, paste it down just below, that this is, and I'm not going to bother with the squares now, I will do, but basically it's the square root of all of this stuff here, like that, you know. Oops, that can't be. There we go. To be careful about when you have the superscripts, but basically it's C is now the square root of A squared plus B squared, so that's basically what that's referring to. So LW is quadratic with respect to our function, so that was our kind of like loss function. Anyway, given, let's have a look. Here's a little image. You know what's our image showing? Given a basis of functions, blue, which is our blue curves. So these are all of our blue curves, and a training set, which is the black dots. We can compute an optimal linear combination of the former red curve to approximate the latter for the mean squared error. So the loss, which is this L of W, is a quadratic with respect to the WKs, and finding W star that minimizes, so I didn't mean to do that, that minimizes it, boils down to solving a linear system. So it's quite mathematical, like mathematically abstract. But if I did type in something for the formula for a linear regression, so double tab to sort of go with it, no, I didn't get it right, there we go, just click on it and go there, sort of like linear regression formula. Let's have a look if we got a formula there, kind of like, where is it? Linear regression, I wonder if we got one there somewhere. I want to, so a linear regression has an equation like y equals x plus b. That's what we're trying to achieve, but where's the actual formula for it? That didn't help, that one. Simple linear regression, let's have a look here. Actually want to find the actual formula for it somewhere. I'm going to hunt around until I find it. That's a bit ugly. Well, okay, that's the best bit. That's the best I'm going to do now under quick notice. But basically, in very simplistic terms, we need to find, we're finding this beta, right? What we want to solve for is we know what our x bar is, which is our average value of x, right? So our x bar, I'm going to draw it on here, right, is this kind of like, I don't know, it's here somewhere. That's our middle value of x, and our y bar is our middle value of y. So something like that. And what we're trying to do in our linear regression, at least from our slopes, is we're trying to find the x minus x bars such that, and the y minus y bar such that we minimize our errors divided by the x minus x bar squared, so like our least squares kind of process. And that's probably the world's worst description of that. I wonder if I can find a cleaner version of it. Information. Sometimes these things tend to overcomplicate it because it's a lot simpler than that. What is this? Ah, here we go. Let's have a look. I wonder the magic of a linear regression. I actually want to get the. No, don't want to go there. Don't want to go on LinkedIn. Get off of LinkedIn. Send me. I want to actually get the form. What I wanted to actually pull out is a mathematical formula for it. I don't know why it keeps on going to LinkedIn. Interesting. I might have to pull up my own work on it because it might be a bit cleaner. There's got to be some good stuff on linear regressions here. Well, there's actually a video tutorial, 30-minute tutorial on linear regressions. I guide you to that. This image is quite a good one because it's relatively simple, but it doesn't have the formula. But I could sort of like describe the form. Everything keeps on linking onto LinkedIn all of a sudden. Why is that? No idea. Oddest thing ever. Oh, here we go. Is there something written on here? Very blurry. Something written on this one. Yeah, okay, here's some best practice. We're not going to get too deep into it, but let's see if we can get some formulas. This is our best fit line. These are our data points. So that's kind of like our line of regression. And where are we on here? What's this? Okay, for some sort of example, I guess. And because literally we can work or do this. The above equation, the equation for multiple linear regression. Hold on, let's have a look. Is it here? Y equals mx plus b. We can calculate the mean. The MSE stands for the mean squared error, I presume. So yes, is it this? I've clicked on that by accident, but it's popped up quite nicely. The yi's, so the distance of any given point, because each of these points are like one of, I don't know where it jumped from on that. I can't even click the back button. I wonder where that came from. It didn't come from that. Did it come from the toolbox in? No, okay, let's click on that again. Right. I kind of opened it. Next time I'll open it in a new tab. But basically, any one of these points, so you take one of these points, like that dot there, and so that's like one of your yi's, and we know the mxi, so we need the xi, and we know, so once we know the xi, we know the slope, and we know the intercept. So it's that difference effectively. We take that difference and we square it. Why do we square it? It's because we want to get the absolute value. Why do we want to get the absolute value? Because a dot below the line is also outs, and it's not like the positive outs. If we just did a simple summation of them and didn't do like a modulus or a squared, so we do the square and then take the square root because the square gives us the positive number. But if we didn't do like an absolute or a square of the square roots, then the positives would offset the negatives, and we don't want the positives to offset the negatives. We want to actually have an error value, and we want to try to minimize and solve for this. That's the process of the linear regression. So that's basically what it is pictorially. So let's go back and continue. It's LW is quadratic with respect to that, minimizes, and it boils down to solving a linear system. For an example, with Gaussian kernels, okay? Gaussian distribution, I imagine. It says see figure 1.1. I wonder if I do jump to that figure, what would actually happen there? So hit close there. Okay, fine, this is the figure, right? So see this example above, okay, for an example with Gaussian kernels. So that's kind of like basically it. The mathematics is abstract. The like general mathematics is abstract, and then the actual mathematics, coding it, or like the true value, like working it out on a pen and paper, is much more like. And actually, one of the things to do, and maybe we'll even try to do it, is compute. I wonder if anyone comes on here, and if anyone does, and sort of like asks, we can work out a mean, and we can work out. So we could do these things on our calculators and our phones and all the rest of it now, but we could like do it in code, and I could show how to do it. Maybe I'd have a little bash at some of it. A lot of it is done out of the box for us. So sort of like. I wonder if we've got an average. No, but I could be like hugely lazy here and do import math. All the imports go at the top, right? I could probably do Skype or NumPy as well, but I think we might have already math, not main, math dot av. No. I guess we'll have an average straight on a list, so we'll just make another function, our test, right, so something like this, and then imagine that we did have this list of numbers, 1, 2, 3, 4, 5, 6, there we go, and then x dot, no, okay, so don't even get an average there. Okay. I wonder if it's stats or something like that. So I'm just going to go here. We'll start using it. So oops, I should be typing in here so everyone can see it. Work out there. There we go. I'm just going to do it computationally because it's quite nice to have it to hand. So imagine we got this set of numbers. There we go. Their numbers are better than my numbers. Okay. We could do it this way. This is really breaking it down. I might actually kind of like, just for the purpose of. So I'm going to call it our average. Right, is because there's other ways of doing this, but basically it's saying something like, and our average just takes in a list, so numbers, which is a list in Python, so it's literally something like this, and this will be all in the box. So it takes in a list, and we're going to do something like, so now we will call this function from elsewhere to test that our list works. We'll take this out and we will paste it in here, and then we will do something like numbers, and because it's a list, I'm hoping, I wonder if no, okay, so for num in numbers, oops, how about indenting it properly, so for num in numbers, okay, total is equal to num plus equal, so total is incremented by numbers, and our total actually before we enter the loop, so total equals 0, so our total starts at 0 before equal, and it keeps on getting bigger and bigger, and the final bit is how many numbers do we have, and there's a little function for the length of our list, whatever size the list was in. So here we've got 6 numbers, but we could have had a different list. I'll copy the list out of here. 1, 2, 3, 4. Yeah, here. Okay. You know, we could try with 2 different lists here. Right. We can even call them x1 and x2. Right. We can see that these lists are of different sizes. This is got 6 items in it, and this has got 5. You know, I'll make this one like. Right, so 1 big list, 1 small list, but basically we want to get len of numbers. This is the full process of everything, and our average, so we're going to return, but we could actually say, let's say our average is equal to the total divided by, and we can put, I guess, count. Right, is equal to, and then total divided by count, right? So that's kind of like, this is the full process, sort of like of calculation. We don't need to do this because it's all given to us, but we can return this, right? Return average. Right? This is the entire process. Now, like, why do I do that? Because like we can work out the average, we can also work out the differences of any given point from the average, which is our x minus x bar. Now, we just test this function out now because we could literally stick it in here and we can get our average of, let's say, x1, right? And if we run it and you know, we just call that the result is equal to this, and then we would like to print our result. So we'll print our result. We could kind of run this little piece of code. Now here we go. Our first piece of Python code. Really, it's too simplistic for machine learning, but it's there, and it's running. And there we go. We get 5.5. That's sort of like average of x1, and you know, we could do the same thing again over here, and you know, this could be x2 and this would be x2, and we could run it again and we'll get 2 different averages, and average of x2 now is 15 and average of x1 is 5.5. So we've got that, but like, that wasn't enough because we haven't got to our least squares part, and so we might want to get the difference between any one of these points and the average that was computed. That's the whole point of this. So we could do like a def, called it least squares. Kind of like a least squares in 1D, because we're not looking at an x and y component here. Least squares, I'll call it 1D. I don't know if we'll do a 2D version, right? But it's going to be something like this, which will also take in a list. So it's going to be numbers, right? But the first thing that it's going to do on numbers is it's going to work out the average. So it's going to work out the average, and the average, now we know how to do it because we've just done it up here at the top, kind of like in our example. We can just say that it's our, we know that it works because we've like tested it already, but it's our average of the numbers, right? Okay, so we can work out the average, but now we want to work out the least squares. So, and I'm just going to jump back to this actual document now. Like, what does this all mean? I wonder if this is the place to do it. Let's have a little scroll through. Not really. Okay. Okay, that's underfitting and overfitting, which I guess we will get to. Yeah, okay. I'm not going to jump back to the document, but I'll jump back to something like this piece here, which is, and so I'm debunking the complexities of this. This isn't as complex as you think. What does this all mean computationally? this means kind of like, okay, and I'm not doing it with it, I'm just doing it simply on like a linear thing. So imagine that we're only looking at the x component, so like we're now just looking at a bunch of dots here, so like there and there and there and there, maybe like loads of them over here, and we're just kind of like saying, well, what and one over here, and we'd say what's the average and what's the mean distance kind of like from that, you know, there, and what's that mean distance there, and what's that error over here, and like where should we put this line such that all of these lines hit their minimum. Now if we put it over here, that wouldn't be great. So we know that our line should kind of like be there, and like let's find that solution. This is the 1D version of it, and this is computationally what the 1D version of it is, and that let you extend it to the 2D version. But that's basically what we're going to do. What I might do quickly as well, so I'll jump back to the code as well, is just at the code, because I am going to pull out afterwards, because all of this stuff is inbuilt in Python. I think it's built in lots of languages, but Python kind of like leads a lot of the way for some of this stuff, so I might just repost that. Doing best fit lines. We're doing the best fit lines bit now. Okay. So let's just go back. We've worked out our average. We know how to work out our average. We know our average function worked over here. We're going to have inbuilt ones, although I thought it was in math that we could get it, but we'll get it in a different way. Anyway, I'm going to put it up on. I pulled this one out of out of Claude. It's quite nice. But you know, that's sort of like the full calculation explicitly as it was, but there's modules that do it before. I'm going to actually a module. Something like that. It's going to be a stats module. I actually really thought it was in the math module. So I'll wait for it to pump out the answer. Oh, there we go. Okay, so import statistics. Yeah. Let's just do that then. This is all built for us. And this comes shipped with Python as well. Probably could have guessed it was doing stats or something stat, and it would have already pulled it up on the import. But it's quite nice to do it the long way, because you're sort of like forced to have a good understanding. So average equals our average of these numbers, and then what we want to do is we want to find the find. So nice little comment, mean square. Notice, like when I did say the mean square distances, it's just one technique that's used, like, and it is the only technique that's kind of like used. But you don't have to. You could actually find the absolute value, and not worry about the square root of the squares to compute it. The absolute value would kind of like, you know, it'd be good. It'd be fine enough, because it'd be our understanding. The model would be just slightly different. That's all. It'd be good enough for finding what in our parameter, what is the minimization function at least, and that's all we're really seeking. So, but the common way is to do the square root. So let's just do that. So we're going to have to loop through. So for num in numbers again, right? We're still going to have to loop through each item in our list. The reason why, the prescription's right here, right, is saying this sigma I equals 1 to n is effectively like a for loop. You keep on doing it through each of the elements. That's basically what you've got to do, and follow this prescription, which is for num in numbers. We want to get something like the diff, right, is equal to num minus, and then average, right? Now we've already computed the average, because the average was computed up here. It's our average. It was the average of all of these numbers. And what we're going to do is kind of like squared, and then we could do effectively is, I wonder if the square root comes first on that. It's the sum of all of these squared divided by 1 over n. In fact, it just squares it. Again, that's sufficient because we're just going to find the minimization point, basically, where the lowest value of that is. And then we're going to do, and this 1 over n piece over here is just, we're going to divide it by the count, because n just stands for the number of items, because it says it actually down at the bottom, number of observations, that's our data points, so it's 1 over n. So we're going to do the difference is all of this, and then we are, so we've worked out our difference, which is the sum of the differences squared, okay, or each number minus its average squared. And again, we've got to plus equals, right? So our diff is going to start out at 0, and it's going to go through each item one by one and increment the item, or increment the difference by this number minus the average squared. So again, so if it's above the line, it's going to treat it, if it's far above the line, my pencil, if it's far above the line, so over here, it's going to be really punishing because that's going to be a high number, right? And if it's far below the line, like over here, right, I should actually draw it in 1D, not 2D, because we're working out in 1D. It's also going to be punishing. Now, if it's just a little bit above the line, like over here, it's not going to be so punishing because this x minus x bar thing here squared, or x, this difference here, this square of this line is much shorter. And likewise, if it's really close to the line here, right, is that, and in fact, if we did have a point that was actually on the line, right, so like over here, that lies exactly on the line, the number minus the average would actually be 0, and we'd square 0, so it wouldn't add anything to the difference. So if everything lay on the line, we just have a straight line. With our best fit line would have a very, very low deviation from anything, so we wouldn't be solving for very much. But anyway, let's continue on that. So we've got our difference equals 0, and then for that, so our difference is now incremented by the square, and then finally we can get our what are we actually calling it here? Our mean squared error. So our MSE, which is our mean squared error, is equal to diff divided by, and again it is the exact same thing here, because we've got to count all of our items, because that's the number of items that we've got, and it's going to be divided by count. So, oh sorry, yeah, divided by count in our case, right? And then we can just return MSE, the mean squared error. Now, okay, one thing that you can do in Python, there's loads of stuff. I'm making this very, very explicit. One thing that you can do is kind of like, you could just return this straight away. You didn't have to compute it, return it. Some people say it's cleaner, some people say it's shorter, I don't know. I prefer to actually explicitly calculate it here, at least for what we're doing, and do it. So we've got this function, we'll docstring it properly, work out the average of the numbers. And here is kind of like work out the mean something like this. So this kind of stuff was done, you know, some of like 25 years ago, but actually 50 years ago, and actually even before that 75 years ago. You could do those calculations, not for huge numbers, but you could certainly do it on paper, and on like fundamental computers. You could start doing it, you know, in the, I don't know, 90s basically, or the 80s, because computing came about, and you could at least do some simple stuff there. So let's just actually run that to start with. So we're going to get our average of, you know, x1 here and our average of x2 over here. So we'll get the same type of thing. I'm going to close this piece for the moment. And I might actually, I might even hit clear over here. Clear. There you go. We don't need this. I might even remove the terminal. Control J. We don't need the terminal. and I'm just going to run it. If I do control, I'm going to use the interactive Python, which if I just do, I guess I'll do it from the top. I'll just stick that in there. It puts it all in one big thing. Right? I could split it down into modules, but basically I run it on the side. It's kind of like sometimes it's just a little bit cleaner to do it this way because you get these little modules with the answers. It's connecting to the kernel to run. So it only does the connection once and then it's good to go. Wondering why it's slow actually. Normally it's a lot faster. There we go. So we've got the average of x1 and we've got our average of x2 from before. But now what we want to do is we want to get the another result, which is the least squares 1D, and we could get the least squares of x1 there, and so like, we could print out the average of, or when we're printing out the least squares of x1, right, which is going to be that result now, and we could even get the least squares of x2. That's assuming our formula works. So x2, we might throw ourselves an error somewhere, I don't know, because there's a lot of code. Normally I test a lot more. So something like this. Yeah, we did throw an error. Object int is not iterable on, where is it, line 41, least squares. How about that? Okay, that's okay. That's a basic error. So run. There we go. I'm going to just delete. The nice thing about this is you can delete the chunk of nonsense that you've done. I think that's deleted it. There we go. It's a lot cleaner. We get our least squares, and we get our least squares here. And notice that the least squares on this one is bigger than the least squares of this one, and that's because these ones are all clustered, so they're all much closer together. So we've got some kind of description just from our least squares. Now, this was our kind of like our own manual calculations. So print sort of like our own calculations. That's what these ones were. But now we can sort of like, we're given all of this stuff, so we can be really lazy because we stand on the shoulder of giants. We just imported this stats module, so we can do something like, I hope, result equals statistics dot have. There's probably better ways of. I know what it is actually. I wonder if it comes straight out of the box. Mean. No. But if we do a list, I wonder if it's x1 dot mean. No, I can do that. Okay. I should be much more familiar with this, but mean. There we go. Okay. But notice one thing straight away off the bat, right? I had to build these functions down here, and I sort of built them so we can explicitly see what they do. These aren't efficient, by the way. There's way more efficient ways of doing it, but I kind of built it explicitly so we can see what they're doing. But here, when I put these dots, right, we see we've got mean, correlation, covariance, harmonic means. There's a whole ton of stuff that's given to us out of the box, and that's just in this statistics module. So a whole ton of stuff for alphabetically. We're just going to go for the mean of like x1, right? So now, instead of our own calculations, and this is only using a very simplistic model. There's way better things, but stats module calculations, right? So we've got this same result, and then we're going to have the average of x1, which is actually called the mean, not the average. And likewise, we are going to have the mean of x2 here, which is going to be x2 over here. And we run that, and now we can see we get exactly the same thing. So the computations work. So this is exactly like to not be scared of anything in any way. this is exactly this formula, which is kind of like our least square thing, and that is the thing that is alluded to from our little book over here. We're seeking a solution in some way. We don't know this yet, where we can, where we find this this loss. So, and what we are computing is this loss function, um, this x minus x bar squared, basically. So let's just go back to here, and I wonder if what version of the least squares thing or something that we got. So probably standard deviation might be the closest thing. So we can say result equals also statistics. Statistics dot, and then this might be a closer version because the standard deviation. Well, okay, the standard deviation is full x minus x bars. I'll use the variance. The standard deviation, I think, is the square root of the variance. So we'll take the variance of x1 there, and I'm going to call it, just to be on the safe side, because I don't know if it's going to be least squares. I'm actually going to call it the variance of x1. So I'm going to have to change the wording. If we do hover over it, I wonder if we get the formula, return the sample variance of data. The data should be an iterable of real valued numbers. Okay, that's just like numbers, basically 1, 2, 3, 4, 5, or any number like 1.5, 2.7, whatever. The optional argument x bar. Let's have a look here. Do you have to put in x bar in here? I wonder. Okay, the optional argument x bar, if given, should be the mean of the data. If it's missing or none, the mean is automatically calculated. Well, guess what? Like we want to set, we don't have to do anything, right? Because so we never had to do this. Yeah, we didn't have to feed the average in. The average was given to us. Now, if we had fed, what's interesting, if we had fed our version of x bar and our version of x bar wasn't the right version, then that number would actually be higher. So I'll actually, that's quite an interesting one to put in here, because I never use it, right? But I presume if we run it, let's get our variance here. We've got 9.116. So it's not exactly the same calculation, but I'm not too worried about that, because what we could show is this. So this is from our stats module. We know that the mean is, where is it? Over here. The mean is 5.5. So if we did this again, right, but this time in our variance thing, we put comma and then x bar. If we put in our original result, so the result from here, which is 5.5, we could actually put in result because we literally calculated it above. That would evaluate to 5.5. We're still going to get the same result of the result, which would be our variance here. So oh no, hold on, no, I've got to be careful. I will actually put in the 5.5 over here, right? We'll get our variance. But I'm going to extend this a little bit, so we'll see, right? When we run this, we do a control return, we get the same 9.166, but the minute I start to move this away from 5.5, so this says like, I don't know, 7.5, right? And run it, we see this number is bigger. Well, hold on a minute, let's try this then in that case. So we do a for loop, right? I in range, I don't know, let's just do a for I in range. We'll go from 0 to 10, that will suit us down to the ground, because that kind of like goes around the 5.5. And we're going to print a whole bunch of variances. So we could do something like print, we're going to test variance against x bar, right, which is our means, our perceived means. So we're going to do it, and we're going to get a whole bunch of these things that pop out. I wonder if I'll actually tab them in, so I can do, I think it's a /T. I've never used that before, but I will. /T, I think that's a tab. So it just like look nicer in terms of the result. And here now, instead of doing 7.5, we're just going to pass in I, like what we trace. It's going to start at 0, and it's going to do 1, and it's going to do 2, 3. It's quite simplistic, but it'll be good enough. Because let's just run this. And what we see, right, if we have a look here, is we've got this big number, and then it goes down, down, down. Then we've got the small number, right? And then likewise, we've got this, so like, then it gets bigger again, right? And it hones in at a point at some point, which is roughly around the 5 level. And actually, what we could actually point it is, if we rerun it, so do it one more time, so with x bar equal to, and I'm just going to put this into an F string now. I, right, we can literally see this come out in the results, which is over here. We've got 0, then we've got 1, 2, 3, 4, and here between 5 and 6, somewhere here is our least squares, right? So that's the process that we're doing. We're honing in, and we're trying to find this over here. We're literally trying to find this where the loss, where that's minimized. So we've now done it. All we've had to do is go through and, like in our 1D version on our very simple thing over here, is we can find our least squares. And the same thing, we could do that over on, for x2. And I think we could probably pass it in relatively quickly and get everything working in the same way. And I guess it should kind of like hone in, like if we did it, like, it should find it being around the 15 level, I guess, in the same way. Not should, it would find it being around the 15 level. So that's kind of like that little section. Now, let's have a little check of everything. We're still streaming and running. Let's scroll on. So under and overfitting, right? A key element is the interplay between the capacity. Between the capacity of the model, that is, its flexibility and ability to fit diverse data, and the amount and quantity of the training data. When the capacity is insufficient, the model cannot fit the data, and the error during the training is high. This is referred to underfitting, so you just basically haven't got enough points. And on the contrary, when the amount of data is hold on one sec. Okay, anyway, on the contrary, when the amount of data is insufficient, as illustrated with an example in figure 1.2, which is an example, the performance during the training can be excellent, but unrelated to, this is what threw me, right, but unrelated to the actual fit to the data structure, as in the case of the model. So kind of like if you didn't have enough points, you might accidentally think that you had a good fit, but really, like, that point should have been there. But the points that we used didn't seem to have much error, so we were cool with it. But it wasn't actually. We really didn't have enough data to do a proper fit. So this whole section was missed, and it was like, oh yeah, it's fine. And then if we did our test over here, it still looked fine. And then finally, when you ran it in the world and you did this one, you get this outlier somewhere, and that's a bad model. So it says if the amount of training data, the black dots, is small compared to the capacity of the model, the empirical performance of the fitted model, which is the red curve during the training, reflects poorly its actual fit to the underlying data structure, the thin black curve. So we wanted this thin black curve, but we didn't get this thin black curve. We got like this red line, which didn't mimic the thin black curve that we wanted to get. And consequently, its usefulness for prediction. So, yeah. Let's just follow on that. The model, okay, and in that case, the model will often learn random noise present in the signal. So basically, it's thinking that some of that random noise actually belongs in our signal, when in reality it wasn't the case. So this is referred to as overfitting. I thought it was underfitting for a second. Oh yeah, okay. So on the contrary, when we've got too much data, we'll get overfitting. So for the same reason, because we've got too many dots. This should be a nice counter. Like, I'd have liked to have seen this have another version of the dots where there's too many dots for the same reason, and you get some sort of overfitting. But anyway, I guess that's that. Also, like overfitting, you're going to have too much information coming into the system too, because you've got too many dots, and you know, a whole part of it is to get the number of computations correct. Otherwise, you slow it down. Even for, like, you know, a big computer. Remember that the data is big, so whichever system that you've got, your computation system, you can always overload it with data, and it will slow down your algorithm. So it's a case of having not sufficient that you haven't got insufficient amount of data, and also sufficient that you haven't got too much that overloads your calculation processes. Because it's got to do this process here, a reminder, which with a sigma 1 to n, and if you pile it up with loads and loads of numbers, you've got to perform this calculation loads and loads of times. Now, in our Python version where we ran it over here, we don't get a time for how long it runs, although we can compute it. It's going to run in a fraction of a second. I guess I will import time, you know, and even for like our most complicated version, which was this, we could do something like t. In fact, for the whole damn lot, we could just start up here, and we could say, so this is everything that we've done. This tiny amount of calculations for a computer, but lots of calculations for a human. T naught equals time dot time. So that's our starting time, basically, and somewhere at the end of it all, we can say that, in fact, I might not even call it the main module anymore. So we will call it run things. Right, and from our main module, we're going to call it run things. There we go. Right. So now, before our run things module, before even running it in our main module, we could do, just so it's a little bit easier to see visually, we could start here at least, shift tab, we could start with a timing, and then we could do the same thing over here, which will be our T1, and then we could do something like print the time taken for everything, right? Everything is basically round of T1 minus T0, yeah, and then it'll be seconds. Right, that's how long all of this is going to take, right? So there, we can run it. And we can see here it's taken 0.0 seconds, right? It's that fast, right? It's literally like 25 decimal places, right? It's taken this fraction of a second to run, right? But imagine that we had, like, you know, a million numbers in here. All of a sudden it'd be a very different story. So, so if this n was large, this n here is large. We're going all the way up to like our big n, it would slow down. So the overfitting wouldn't be helpful for us. It would slow us down. So anyway, so a large part of the art of applied machine learning is to design models that are not too flexible yet still able to fit the data. This is done by crafting the right inductive bias in a model, which means that its structure corresponds to the underlying structure of the data at hand. So we kind of like need to have an intuition of what we're fitting. So kind of like wonder if we can zoom in on instructive bias there. There was an instructive bias machine learning. In machine learning, inductive bias refers to the assumptions or perceptions that a model or algorithm makes about the underlying distribution of the data. It's some sort of base thing that we can start with. These biases can influence a model's ability to learn from a given data set and can affect the performance of the model on the model on new unseen data. So yeah, if we're expecting things that we bake into the model, they might learn a little bit better, possibly. I don't know, is there an image that's useful? Inductive bias of a model, possibly. I don't know what this model is going to show us. It's going to take us to another page somewhere. Okay, it's not that clean, so I'm just going to remove it. But if we've got, I mean, here in our image, you know, here's our training data, and this is a good optimum because our inductive bias is guiding towards us. And here our inductive bias is guiding us somewhere away from our good optimum. So something as crude as that, really. But that's kind of like the idea of it at hand. Anyway, even though this classical perspective is relevant for reasonably sized deep models, things get confusing with large ones that have very large number of trainable parameters and extreme capacity, yet still perform well on prediction. So at some point it goes out of our hands and we can't tell it what to do, and we've got to trust the machine learning to sort of like do this. And it says we'll come back to this in 3.6. What section are we on? List of figures. Well, that was list of figures. That was a foreword. We're on page 17. Okay, 3.6. So, but on page 47. So 30 pages later, we'll come back to it. So we were on page 17. We've done 10% so far of what was of the book. We've done 10% of the book. Another 90% to go. I wonder if I should stop here and continue. How long have we been going for? 2 hours. Might be. I might force a stoppage. I don't know. Categories of models. Let's have a look. I might force a stoppage just so I can pre-read a tiny bit. Let's have a little browse through. Categories of models. We can organise the use of machine learning. I might stop this and then restart it just because I might bring out some of my stats. And I don't need the fumbling around because I do cover some of this stuff. Let's have it. Well, anyway, we'll have a little perusal. See, categories of models. We can organise the use of machine learning models. We can organise the use of machine learning models into 3 broad categories. Right. Again, like the images and stuff that we get on the web is a little bit better than that's in this book. But if I can just about highlight them on one page. So like, you've got regression over here, right? Whatever regression is. Then we've got classification over here. I think there's more categories in this, quite frankly. But again, this is a summary book. And then we've got density modeling over here. So something kind of like that. So there are 3 broad categories. So let's go and have a look anyway what they are. Regression, which consists of predicting a continuous valued vector, okay, y exists as a set of real numbers, I believe in the k-space. For instance, now this is like mathematically, the mathematical notation is some sort of like, oh, it looks really difficult. It's just a whole bunch of real numbers, basically, like 1, 2, 3, 4, 5, 1.1, with decimals, whatever. It's just a bunch of real numbers. It's mathematicians' way of saying a bunch of real numbers. For instance, a geometric progression of an object given an input signal x. Okay, what's a geometric? I'd say a geometric position of an object given an input signal x. This is a multi-dimensional generalization of the setup we saw in 1.2. The training set is composed of pairs of input signal and a ground truth value. Okay, we could look up what ground truth value means, possibly like later. So that's our first session, which is regression. Then we've got classification, which aims at predicting a value from a finite set. What is a set here? We've got Python set. I'll talk about a Python set in a second. A set. So 1 dot 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 all the way to C. So a different mathematical notation, but it's just a set of numbers. For instance, label y of an image x. Okay. As with regression, the training set is composed of pairs of an input signal and ground truth quantity. We need to know what this ground truth quantity is. Here a label from, and here a label from that set. The standard way of tackling this is to predict one score per potential class. So the categories, or the classification, we sort of put them like, is it square, is it triangle, is it circle? We turn square into 1, triangle into 2, circle into 3, so I put them into their categories. And we see that these clustering types of things, that's kind of like what that is, and put it into clusters. Hopefully we'll get into that. And then finally, I guess density modeling has its objective to model the probability density of a function of the data, mu of x, which means the mean values of x for itself, for instance, images. In that case, the training set is composed of values xn, which is a whole bunch of values, x0, x1, x2, x3, x4. There could be a bunch of numbers without associated quantities to predict. And the trained model should allow for either the evaluation of the probability density function or sampling from the distribution, or both. Both regression and classification, so the first two, are generally referred to as supervised learning. Okay, since the value to be predicted, which is required as a target during training, has to be provided, for instance, by human experts. Okay, it could be our x bar in our case, in our model here. The value to be predicted, and we cycled through, and we guessed at all of these numbers, but actually it turned out anyway to be our mean over here. But we could put in a whole bunch of numbers, and it would solve to getting the least squares, lowering that L of S function. So, on the contrary, density modeling is usually seen as unsupervised learning. Ooh, all of a sudden the computer's learning on its own, or we haven't told it things. We're no longer capable of guiding it, since it is sufficient to take existing data without the need for producing an associated ground truth. So all of a sudden, we're moving away from this model and going to this model where we don't have a ground truth. This one guided us, and now we say we don't even know how to guide ourselves, so let's not do that and let the model will find that if we could guide ourselves, in fact, in the wrong way, so let the model determine and put the inductive bias, so the model will do the inductive bias and guide us that way because it knows better than we do for various reasons. So that's kind of like what it would be. That's the unsupervised learning. So this one here is supervised and this one here won't be supervised. It's kind of like fundamentally the difference as it's been described to us, at least my interpretation of it. So see, these three categories are not disjoint. For instance, classification can be cast as class score regression or discrete sequence density modeling, as is iterated classification. Furthermore, they do not cover all cases. One may want to predict compound quantities or multiple classes, or model a density conditional on a signal. This is hard because there's lots of words and not that much in terms of kind of pictures paint 1,000 words. I know that you can put pictures in a book, you can't put videos in a book. So it's quite wordy. There's not enough mathematics potentially, so I've drawn a lot of the mathematics to simplify and make it helpful. But then again, we have to bear in mind that this is the little book of deep learning. So it's not the big book of deep learning. It's kind of designed for a mobile phone. So we're sort of like reading through it and getting to our point. But anyway, it goes to the second chapter, which is efficient computation. And actually, I thought I was going to stop here, but probably I'll stop here just because maybe it makes sense to do it chapter by chapter. Density modeling. I was going to talk about the set. So a set is quite a simple thing in Python, which relates to things that we did in school. So like F. I'm going to put everything into functions. Right. What sets are, right? But really, Python gives us out of the box data structures very well. One of the nice things about it. And one of the data structure is something called a set. You can do this in two ways, right? We can make this set, S for set, right? I like that, but equals, and then we can just do these curly braces, and we can do like 1, 2, 3, 4, 5, right? And one of the nice things about all of this is I think that I was in the wrong bit here. Let's get rid of that. Control X. How about, had the wrong thing open. Let's go back over to here. There we go. We're going to do our set still. We'll do it over here, right? And a lot of this stuff now, I get run things. I'll make another function called run more things maybe. So we're not going to run things anymore, right? So we can, so like, this is quite nice because we can time it anyway. Not that we care about the time. But if I comment this out, it doesn't get run. This entire function doesn't get run now. So we're just going to like look at sets, right? Here we've created a set, and then we can print our set there like that. And if we run it now, nothing, because we haven't put anything in. We're going to run our what sets are. Okay, so let's just run that now. What sets are, right over there, and we run our little thing, and it says 1, 2, 3, 4, 5. So nothing actually happened at this point, right? But now let's just do this, which is we take our same set like that, and do 6, 6, 6, 6, 6, 7. Oops, 7, 7. Can't leave blanks. There we go. Right. Something like that. I haven't been great with the spacing or whatever. We now want to print our set, and we see that we get 1, 2, 3, 4, 5, 6, 7, 8. Right. What's happened? The set has thrown out duplicates. So in Python, a set is a collection of unique numbers. Now it also lets us do this. So if we had a list in Python, so we could have the same thing. So all of this in our list. In fact, we can take a list from here. So let's just take this list here, this x1 over there. And so let's paste it over here. So we've got our x1. Let's tab it across so it's in the right space, part of the function. And then we can do s again is set, and we can pass our list in of x1. So x1, right? Now, again, these are all unique numbers. So when we do print s, right, we're going to get two sets here. The first print is going to be this set, which we already know gives 1, 2, 3, 4, 5, 6, 7, 8. And our second set will be the second list over here, right? So we can convert a list, which is a data structure in Python, into a set. And it's going to be a bunch of unique numbers. Now, again, if our list had a second 10 in here and another 10, for example, the set comes again to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It's thrown out all of the other 10s. And we see these things, and the reason why it's like this is, like going back to our school days, a set was kind of like this thing here, you know, and then another set was something like this thing here, and you might have even had, you see we've got this little overlapped bit, so we can have overlapping sets. We could have another set here and you've got some more overlapping, and we could even have a set here which has got triple overlapping over there. World's worst the world's worst drawing, but nevertheless we get that. There we've got a triple overlapping, we've got some double overlapping over here. If I highlight it in green, it's like greens and blues, there we go. And some double overlapping here, and some doubles here, and where the blue was, it had triple overlapping. But anyway, that's our sets, and that's where our sets intersect. These are called intersections, and I guess this is like a triple intersection because it's where three sets have intersected, and here's one more. So I forgot the other petal of our thing because we created that. So we've got these intersections, and these bits here are yellow. There's like, this is part of the set. There we go. So we can now not only have sets, but we can do things with sets. We can intersect them. We can join them up at certain points. But that's what sets are. That's what it's referring to mathematically when it's talking about. So all of this stuff here is what's being spoken about in the book over here some way in our classification. And we're trying to put these things. Imagine just one more, which is basically that this is more like a distinct set, so these things are separate from each other. So we've got one over here and one over here. They've got nothing to do with each other anymore, right? These are like squares and these are triangles. Everything that fits in here is a square and everything that fits in here is a triangle. Or males and females, they're not even interlinked, although like now in the modern days you can have males and females that are interlinked. They're completely distinct sets. If we get a data point that's kind of like over here, or over here, or over here, we're going to say that belongs to this category because it's closest to this category. This one's inside the category, so we're quite sure it's that. This one's still closest to there, and this one's closest to there. But if we get a data point over here, or over here, here, or here, that belongs to this category over here. And then we're going to say we need, well, what happens if we get a data point that's all like there, right? That's problematic because there's some sort of intersection, and now we're saying, and there's some sort of standard deviation around these sets, right? So like there, that we're quite sure what these ones are, and we're quite sure what these ones are, but things out here, if they lie on this side of the line, you know, it belongs to, you know, it's all part of this section over here. But if it lies on this side of the line, it's probably one of these. But we're very confident here, and in this section here we're less confident. So that's kind of like what this classification thing and these sets are talking about. So it's kind of like the back language, and we're setting ourselves up for sets. There we go. Setting sets. So let's just go back, click on that. So that's our classification, and we've got our density modeling, which is I guess some sort of like, you know, our normal distributions or like probability distributions around those sets as well. So I just might just take this last bit, copy, before I sign off, and go back and stick out what a ground truth is. So let's have a look. Ground truth. Here we go. Ground truth is information that is known to be real or true, provided by direct observation and measurement, as opposed to information provided. Okay, so it's our actual like inference of something. So in our simplest case, where we worked out x bar, like we know that to be the mean, we could call that, we could say that's our ground truth now, and the differences from that, you know, the xi minus the x bar. That's kind of like our basis. So one is our like truthing, and one is kind of like, you know, they're the variances from the truth effectively. So yeah, it's kind of like a math word that's inherited from the English language, or probably the English language were inherited from the math thing, but that's like the synonymous meaning of it. So I think that's pretty much it. It's referring to mapping. World object, mapped object, I guess. I'll try to find maybe commonly used ground truth. capturing videos. No, okay, fine. I won't go any further than that because I think we'll leave it there. And I guess that's a lot done, or a lot spoken about. We've read through the first chapter, which is only 19 pages of 160. But I'm actually going to, given that I'm so statistical right now, we've done 19 out of 163, I think. There we go. We've done just over 10% of the book. The next bit is about efficient computation. I think this is a smaller chapter by what we looked at. So, but I'm going to sign off here and continue on at another point. So, anyway, those of you who did watch it, or do watch it, if you do, hit the like button or the follow button if you found it interesting. In fact, if you didn't find it interesting, hit the like button and hit the follow button. And if you really didn't find it interesting, send it on to somebody else who you don't like, or watch it before you go to sleep. It's good sleeping material. I often sleep when I've got these videos on, and then wake up a little bit cleverer. So yeah, just do that. Like, follow, subscribe. Questions, comments. I'm sure that I said a lot of things that were wrong or missed stuff out, or where you can add to it. So definitely put all of those things in. And anything that you might else want to see. Otherwise, I might continue with this and keep up. Probably read right to the end of this book and go through all of the components of it. So I'll leave it there. Sign off and yeah, subscribe.